Hi students, in this video we are going to discuss about Sabine's formula for reverberation time. Sabine's is a units for reverberation time also. Okay, so Professor C. Sabine determined the reverberation times of empty halls and furnished halls of different sizes and arrived at the following conclusions. That means he is just observing the patterns, what is happening inside when a sound energy is produced within the empty halls when it is furnished. So all these things he observed and make some conclusions. So the reverberation time depends on the reflecting properties of the walls, floor and ceiling of the hall whenever it is empty. If there are good reflectors of sound, if they are good reflectors of sound, then sound would take longer time to die away and the reverberation time of the hall would be long. So whenever those are the good reflectors of sound like empty hall, the walls, floor, ceiling, all those, so the time will take longer time to die. So the reverberation time will automatically that is long. The reverberation time depends directly upon the physical volume of hall, physical volume V of the hall. The reverberation time depends on the absorption coefficient of various surfaces such as carpets, cushions, curtains, etc. present in the hall also whenever it is furnished with some items. The reverberation time depends on the frequency of the sound wave because absorption coefficient of most of the materials increase with frequency. That means whenever the frequency of the incidence waves increased, then the absorption coefficient is also increased. So the reverberation time depends upon the frequency of the sound wave because it absorbs coefficient of most materials increase with the frequency. Hence, high frequency sounds would have shorter reverberation time. So reverberation time alpha, that is directly proportional to the volume of the hall V by absorption coefficient A. So the reverberation time T equals to K V by A, where K equals to proportionality constant. Okay, so where K is proportionality constant, it is found to have a value of 0.161 when the dimensions are measured in metric units. So whenever it is measured, the hall is measured, then the reverberation time T value will be T equals to 0.161 V by A. We know that A, the total absorption coefficient, is equals to the sum of n equals to 1 to n an into Sn, where A is the absorption coefficient of each material present in the hall and S is the area of that particular material. Then T equals to 0.161 V by the A will be replaced with summation of all materials. So the Sabine equation works well for large enclosures. Now Sabine's formula for reverberation time. So let us assume that the sound energy is uniformly distributed all over the room. The absorption of sound by the air is neglected. So what we have to do first? We have to calculate the radiation energy from the volume element dV. Now the entire volume is V. Let us assume that the volume, elemental volume, that is dV in the hall, and then the rate at which it is incident on the surface element ds. So the total area is S, we are considering the surface element ds. When the volume is V, we are containing the elemental volume dV of a plane wall AB. Okay, so taking the midpoints of taking the midpoints of ds as the center and radii, that is equal to r and r plus dr, draw two circles in a plane containing the normal ds. So then the two radii are making an angles of theta and theta plus d theta with the normal. I have shown you the diagram. Okay, this is the ds area. which makes an angle theta d theta, okay, having the radius r which is drawn a normal. Okay, we all are discussing about this particular area only. Okay, here I'm repeating it again. Taking the midpoint of ds as the center and radii equal to r and r plus dr, draw two circles in a plane containing the normal ds. Then two radii are making angles theta and d theta, that is theta and theta plus d theta. According to r it makes angle theta, according to r plus dr it makes an angle theta plus d theta. With the normal, consider the shaded portion of the fig lying between two radii and between the circles. We are considering some part which is shaded here. Okay, see, particularly this portion we are taking. Okay, and next, according to that particular area, the arc length of the shaded area is r d theta. Now the radial length, that is dr. Surface area of this element is r d theta into the radial length dr. If the shaded elemental area is rotated through a small angle d phi, the elemental area sweeps through a distance r sin theta into d phi. Okay, the volume traced out by the elemental area dV, that equals to r d theta dr, that is the surface area element, into the entire area element. Okay, it sweeps some angle, that is r sin theta d phi. Now the total volume traced is r square sin theta d theta dr d phi. Now the sound energy present in the volume element at any moment E, at any moment, that is equal to the total sound energy E. So E into the complete value of dV, that is r square sin theta d theta dr d phi, where E is the energy per unit volume. Okay, and next, so this sound energy is traveling through the element equally in all directions, which we are considering the area, elemental area ds and the volume dv. So the sound energy E which we are taking, so that is traveling through the elemental equally in all directions. So energy traveling per unit solid angle, that is equal to E dv by 4 pi. Now the solid angle subtended by the surface area ds at this element of volume dv, that is d phi, d ohm, that is equal to d ohms equal to ds cos theta by r square. This amount of energy that reaches ds from dv, that equals to E dv by 4 pi into ds cos theta by r square. So that equals to E ds sin theta cos theta d theta d phi dr by 4 pi. Okay, so from where we are getting this value, from where? So according to this and the previous value, E r square, here E, this r square and this r square gets cancelled. Okay, so from this, so the total amount of energy reaches ds and dv. Okay, we are getting this much of value. So total energy received by ds in 1 second from the entire volume is obtained by integrating the above expression, that's by integrating this equation especially. Okay, now E ds by 4 pi is a constant, integral 0 to c dr integral 0 to 5 by 2 sin theta cos theta d theta and integral 0 to 2 pi, that is d phi. So those are the limits. Okay, so this value becomes 1 by 2 and this value becomes 2 pi. Okay, where c, that is the velocity of sound and it is distance within the which the whole volume is lying. Okay, now the energy received per second is ECDS by 4. Okay, so if A is the absorption coefficient of the wall AB of which ds is a part, then energy absorbed per second by the area ds, that equals to ECATS by 4. So the total rate of energy absorbed by the wall area is equals to 1 by 4 ECA So the ds becomes s. Okay, so the total rate of absorption of sound energy by all the surfaces of the room is 1 by 4 ec. We know that a, the total absorption coefficient a is equal to sum of a1 s1 plus a2 s2 plus a3 s3 and so on. So we are writing as, the term as capital A, where A is a summation as, the total absorption of all the surfaces according to all the surfaces present in the volume on which the sound energy is incident. Okay, now build up of a sound in a hall. How the sound will be built up in a hall? The rate of growth of sound in a room. Okay, how the sound will, incident sound will grow in a particular area. Okay, so at any instant, the rate of growth of energy in the hall, that is rate of growth of energy in the hall, that is rate of supply of energy from the source minus rate of absorption of all surfaces in the hall. Is it S? 100%. The total incident energy, that means the rate of growth will depends upon the absorption due to the surfaces in the hall. So what is the rate of growth? To know that, we are subtracting the rate of absorption from actual incident energy, that is the rate of growth of energy in hall, that equals to a rate of supply of energy from the source minus rate of absorption of all surfaces in the hall. See here. Okay, so V dE by dt, that equals to total incident sound P minus absorbed sound in the previous session, that is equal to ECA by 4. Now dE by dt equals to P by V minus ECA by 4. P by V, that equals to dE by dt plus this term. Okay, now we are taking that CA by 4V is a alpha and multiply both sides by e power alpha t. Okay, we are doing the same thing here. Okay, dE by dt e power alpha t plus this term is alpha into e power at equals to p by v e power at. So from this term we are getting, so whenever the value CA by 4V equals to alpha, we need V. So for V equals to CA by 4 alpha. That means CA by 4 alpha. So 1 by V means 4 alpha by CA. Okay. Now d by dt of E into E of alpha t, that equals to 4P by CA alpha into e power alpha t. Now we are integrating both sides, then we get the value like this. Okay, the integration differentiation gets cancelled, then the additional term a will be added because this term becomes alpha gets cancelled, we are getting only this. So where k is a constant of integration, the value of k is found using the boundary conditions. Okay, so like this the sound will grow, the buildup of sound within the we are taking a hall, whatever it may be, taking a wall. Next, growth of the sound energy and decay of sound energy in a hall. Okay, growth of the energy density. If T is measured from the instant the sound source emits sound, that initial conditions becomes E equals to 0 at T equals to 0. Okay, when there is no energy, there is no time to measure the reverberation. Now K equals to minus 4P by CA according to the previous case, that is the buildup of sound. Then E equals to 4P by CA into 1 minus e power minus alpha t. Now E equals to EM into 1 minus, where 4P by CA is we are assuming the term as EM. So this equation represents that the sound energy grows in an exponential manner with the time t. So it increases till it attains the steady state value EM at t equals to alpha. Okay, and next, decay of the sound energy in the hall. So let us assume that after a certain time that the energy attained the steady state value, the source of the sound is switched off. Then P becomes 0 and let that instant be taken as T equals to 0. Whenever P is 0, then T equals to 0. The initial conditions would be P equals to 0 at T equals to 0 and E equals to Em. Now K equals to E into e power alpha t. So K equals to 4P by Ca equals to Em. Here also the equation as in the above. So that indicates the sound energy decays, that indicates it decays exponentially after the source of sound is switched off. So you just observe this graph, the growth and decay of sound in a hall, how it will growth and its steady state, and how the decay will be. It is in a, the decay will be in a exponential manner. Okay, let us see reverberation time T. So the reverberation time T is defined as the time taken by a sound to fall 1/1000th of its original value after the source is cut off. That is E equals to Em by 10 power 6 and T equals to T. We get what we get, e power alpha t equals to 10 power 6 alpha into T equals to exponential is in this side. Okay, so now the T value becomes certain value. So taking the velocity of sound in air C equals to 345 meters per second at room temperature, we are getting this value. Okay, so this reverberation time T is directly proportional to the volume of the hull and inversely proportional to the total absorption made by the hall. So let us see what are the limitations. The Sabine's formula for reverberation time gives correct results only when the average absorption coefficient is less than 0.2. So that is whenever the value is less than the 0.2 only, and only the time the Sabine's formula will work. So the Sabine's formula gives contradictory result in case of a dead room where A equals to 1, the reverberation time should be 0. But Sabine's formula gives a finite and non-zero values for reverberation time T equals to 0.161 Vs. That means that much of units of Sabine's. Okay, so in the derivation of Sabine's formula, it is assumed that sound energy distributes uniformly in the room and that there is no loss of energy in the air. However, this is not a practical reality.